Welcome to this explainer. We're jumping right in today to decode the rules of object-oriented architecture in C++. You know, it really helps to think of inheritance exactly like a blueprint for a building. When an architect is designing a massive skyscraper, they don't sit down and reinvent the concept of a door or a window from scratch for every single floor, right? That would take forever. Instead, they create a foundational blueprint and then just inherit those core properties, tweaking and extending them as they build upward. Well, in C++, inheritance lets us do exactly that with our code. We can take an existing class, our solid foundation, and just build upon it seamlessly. So let's grab our hard hats and start decoding these architectural rules.
Okay, here is our game plan for today. We'll be covering access rights and inheritance, overriding base class functions, constructor and destructor execution, the multiple inheritance trap, and finally, a quick summary and key takeaways.
All right, part 1. Access rights in inheritance, or what I like to call the blueprint rules. Think about any secure building. Certain people have access to the public lobby, some can get into private offices, and only a select few can crack the vault. In our code, we need to determine exactly who gets access to what. The inheritance accessibility matrix is basically your ultimate cheat sheet for this. It maps out every single combination of how a component is initially declared in the base class and how it's then inherited. To use it, you just find the intersection. For example, if a component is public in the base class and inherited publicly by the subclass, the resulting access remains public. It's a completely logical grid that clears up any confusion about what a derived class can actually see and touch.
It all boils down to this strict hierarchy. Private is your most restrictive vault, protected is a standard locked door, and public, wide open. This simple inequality literally dictates the baseline security of your data. A derived class can absolutely never grant more access to an inherited member than this hierarchy allows based on the inheritance type.
To put that into perspective, think about how these inheritance nodes actively morph your access levels. Let's say you use protected inheritance. All those public members from your base class, they are instantly downgraded to protected members in the derived class. And if the base members were private to begin with, they stay completely hidden from the derived class directly. You can still access them, but only indirectly via the base class's public or protected functions. It's a remarkably tight, bulletproof security system.
Moving right along to Section 2, overriding base class functions. This is where we start remodeling.
Inheriting functions is awesome, but sometimes the default behavior just doesn't fit the new room we're building, you know? That's where overriding comes in. But here is a massive pro tip for your exams. Absolutely do not mix up overriding with overloading. To actually override a public member function of a base class, your derived class has to use the exact same name, the exact same number of parameters, and the exact same types of parameters. It has to be an identical match, the whole shebang. If you change even one parameter type, you haven't overwritten it, you've overloaded it. Compilers catch this trap all the time, so be careful.
But wait, what if you override a function to add some cool new behavior, but you still critically need the original blueprint's functionality to run first? Well, you use the scope resolution operator, that's the double colon, as your backdoor. By typing the base class name, a double colon, and then the function name, you're explicitly telling the compiler, hey, ignore my new remodel for a second, and just go run the original instructions.
Let's put on our compiler hats for a second and trace this out line by line. We've got a derived object, obj. First up, obj.setB of 7 and 8 sets the derived class variables var1 and var2. Next, obj.setA of 1, 2, 3 calls the inherited base class function to set x, y, and z. Then we hit obj.print. Because class B overrides print, it executes its own version, which outputs var1 and var2. But check out that last line in main, obj.a.print. That forces the program to entirely bypass the derived version and call the original base class print function.
And boom, our mental compile matches the console perfectly. We get 7 and 8 for the derived class variables when we call the standard print, and then we get 1, 2, 3 for the base class variables when we use our scope resolution operator backdoor. Honestly, tracing code like this is for sure the best way to verify you actually understand the architecture. All right, Section 3, constructor and destructor execution, examining the actual memory timeline.
Now that we know who can access the data and how to change it, we have to look at the physical timeline of construction and demolition in memory. You absolutely have to keep these strict rules in mind. Derived constructors cannot directly access private base members, and they can only directly initialize public base variables. But here is the most crucial part. A derived class literally cannot exist without first acknowledging its base foundation. When a derived object is declared, it absolutely must execute one of the base class constructors first. And we specify which one to call right there in the heading of the derived class constructor definition.
The easiest way to remember this, construction is always top-down. Imagine Class C inherits from Class B, which in turn inherits from Class A. The compiler starts at the absolute bedrock. It executes the base Class A constructor first, builds upward to the derived Class B constructor, and finally caps it off by executing the most derived Class C constructor. It's base to derived, strictly in the exact order of inheritance. But demolition? That is strictly a bottom-up operation. When an object goes out of scope and gets destroyed, the destructors execute in the exact reverse order of inheritance. It tears down the newest, most derived additions first, Class C's destructor, then Class B, and finally it rips up the foundation with Class A's destructor. So build, top-down, demolish, bottom-up. Simple as that.
Next up, Section 4, the multiple inheritance trap, are structural hazards.
Having mastered standard construction, we urgently need to talk about a major structural hazard. The instructor actually pulls no punches on this one. They specifically warn against multiple inheritance, calling it error-prone and saying it obfuscates your class hierarchy. In fact, many modern object-oriented languages, like Java and C#, have just abandoned this feature entirely. Why? Because it completely muddles your architectural design and leads to massive ambiguities, like the infamous diamond problem.
Check out how this hazard looks in practice. Imagine a class called sub that inherits from both super A and super B at the exact same time. By doing this, it's forcing the compiler to juggle two completely distinct base foundations at once. So sub now has direct access to both storage from super A and safe from super B.
Sure, it spits out storage equals 3 and safe equals 5 perfectly in this tiny little sandbox example, but remember the warning. In larger programs, if super A and super B happen to have functions with the exact same name, the compiler would have absolutely no idea which one to pick. This dual inheritance creates a total nightmare for debugging and maintaining a clean codebase.
And finally, Section 5, Summary and Key Takeaways. Time for our final inspection.
Let's wrap up with a rapid-fire review of our blueprint rules to make sure you're totally test-ready. First things first, you need to burn this conceptual distinction into your brain. Inheritance implies an is-a structural reality. A car is a vehicle. A subclass is a base class. Composition or aggregation, on the other hand, is strictly a has-a relationship. A car has an engine. It doesn't inherit from it. Actually, using composition is exactly how a lot of modern programmers bypass that whole multiple inheritance nightmare we just talked about.
So here's your cheat sheet. The critical patterns you absolutely must memorize. The accessibility matrix is your baseline security. Overriding demands an identical signature, or else you're just overloading. The double-colon scope resolution operator is your sneaky backdoor to hidden base functions. And never forget the memory timeline. Constructors build top-down, destructors demolish bottom-up.
So as we wrap up this explainer, I've got to ask, when you sit down to architect your very next C++ project, how are you going to apply these rules? Are you going to confidently build a robust is-a hierarchy using safe, single inheritance? Or will you strategically sidestep those structural hazards by building smart, has-a compositions instead? The blueprint is entirely in your hands now. Happy coding.